for the introduction, and at the outset my thanks to the organizers for the invitation. In the next 20-25 minutes I will be showing you our research endeavors towards propargyl-Claisen rearrangement. We know that Claisen rearrangement is one of the fundamental carbon-carbon bond forming organic reaction where allyl vinyl ethers underwent 3,3 sigma tropic rearrangement to give you gamma delta unsaturated carbonyl compounds. The first report on the Claisen rearrangement was published in 1912 by Claisen himself, and in the next 100 years or 112 years lot of improvements and developments have been reported. For example, allyl vinyl to allyl aryl and various substitutions on these systems have been reported, and then the moment we replace the oxygen with nitrogen, it is called as a acylation, thiaclison. And of course, since Claisen rearrangement is the first one in the 1940, Cope rearrangement also published where you remove the oxygen and substitute like N, S and CH2. And then 1972 Ireland Claisen rearrangement is also reported where you have a O acetates and then using LDA in situ you generate the enol and so on. So once you replace this allyl group with a propargyl group or this double bond with a triple bond, that is generally called as a propargyl-Claisen rearrangement. Since 1912, several people tried to attempt on the propargyl-Claisen rearrangement. Most of the times the reaction failed to give the products and always star was the resultant product. But for the first time in 1963, Professor Thiagarajan from University of Madras has reported propargyl-Claisen rearrangement in 1963. Therefore, just like a Claisen rearrangement, you get a gamma delta unsaturated systems, but here you get allene tethered carbonyl compounds. Interestingly, we know that allenes are highly reactive intermediates. You have two types of hybridization, sp and sp2, and then you also have a carbonyl compound. Therefore, one can study beyond propargyl-Claisen rearrangement by performing some additional cyclization reactions as shown here. So our idea on this reaction is to study the propargyl-Claisen rearrangement beyond allenes, and then as a result what you get is a direct access to cyclized products, and at the same time we don't want to start from the propargyl ethers, we wanted to in situ make the propargyl ethers and thus to lead to the cyclization products. Therefore, we don't want again to start with a propargyl alcohols at the same time, because Thorpe-Ingold effect suggests us if we have a gem dye substitution, the cyclizations are much faster than unsubstituted systems. Therefore, we choose a propargyl alcohol of this type where you have gem dye substitution, and then we subject this system to propargyl-Claisen rearrangement to get the cyclization reactions as shown. The idea is that once we have this one propargyl alcohol, under influence of any acid catalyst, we generate a propargyl cation, and if you have an enol of this sort, of course there is a CO bond versus CC bond formations exist. If you consider CO bond formation is happening, then you have a propargyl ether that is in situ formed, and then this undergo 3,3 sigma tropic rearrangement to give you the propargyl-Claisen rearrangement. Now since there is an acidic carbon over here, the system can in situ undergo enolization, and then the OH can cyclize at sp carbon or sp2 carbon to give a product as shown here. With this idea, we started with a simple starting materials like a tertiary propargyl alcohol and beta naphthol, and then I am not showing the optimization conditions, but when we mix these two with a calcium based Lewis acid under solvent free conditions, heat at 110 degrees Celsius, we got the naphthopyrans. In this reaction, we have generalized the substrate scope. You can also make the spirans the moment you have a ring, R1, R2 is a ring, you can make the spirans. We also made a natural product called lepochinol using this strategy. As proposed, we were able to isolate the propargyl ether in this reaction to indicate that this is proceeding through propargyl-Claisen rearrangement, and then cyclization at sp2 carbon gave the naphthopyran. During this process, we also studied some of the Brownstedt acids, and then interestingly, a Lewis acid is giving the naphthopyran, whereas a Brownstedt acid is giving 3-aryl indines. We tried to understand the reaction mechanism, and then we realized again the reaction is proceeding through propargyl ether formation, and then this underwent cyclization to give the naphthopyran. Once naphthopyran is formed, the brown shade acid protonates the oxygen and ring opening followed by cyclization via intramolecular Friedel-Crafts annulation gave the 3 aryl indines. Obviously, we also extended to make several analogs of these products. Here you see when we have a naphthol 1,6-dihydronaphthol, so on both sides we were able to perform the propargyl-Claisen rearrangement on both sides, and then respective naphthopyrons were opened and underwent to give 3 aryl indines on both sides. We were also observed that when we have a system, it is not limited to naphthols only, you can also use fluorinols as indicated here, and once you have this stereogenic center here, these compounds exhibit atropoisomers because sterically hindered biaryl systems we can see on these things. And of course, several spiranes as mentioned here, if you have a cyclic ring over here, you can synthesize several of the spiranes as indicated here. In continuation, we introduced in the same reaction iodine. At room temperature, we saw that earlier I have shown you that there was a hydrogen here on this double bond. Now, if you introduce iodine into that, then you can get iodo systems. And then as a routine practice, we tried to show some synthetic application where the intramolecular etherification to give this kind of a polycyclic scaffold was formed. However, the main reaction that we developed was having a hydrogen here. There was a hydrogen. So then we were thinking that is there a direct way that you can do a sp2ch functionalization to give direct etherification. Basically, I don't want to free functionalize this to iodine and then perform this one. A direct CH functionalization we are looking at. When we looked at the literature, there are some hints that when you have biphenyl systems like this, there are reports that people made corresponding fused systems. And even you have a 2 alkynyl phenols also subjected to intramolecular cyclization. However, we didn't see any report on particular this scaffold where indene is attached. So we feel that this is an opportunity for us to develop a strategy for intramolecular etherification. Therefore, we realized that using these conditions, copper iodide and DMS at 140, we were able to do intramolecular CH functionalization to make this polycyclic scaffolds. Of course, the reaction was quite general, and then for example, if you have a systems like this, the starting material here was showing atropoisomerism because there was a stereogenic center here and sterically hindered biaryl systems. The moment you subjected to cycloetherification, the system becomes a planar and lost the atropoisomerism. And as usual, you can also install several spiranes at this quaternary center. And at this thing, both sides, this side, you can see that 1,6-dihydroxynaphthol is there, so you can do cycloetherification this side and this side to produce a scaffolds of this sort. Then so far what we have seen is aryl propargyl ethers. Then we were thinking about, is it possible to have aryl vinyl propargyl ethers Claisen rearrangement. Therefore, what we thought is, if you start with a 1,3-diketones as shown here, they are readily produce the enols as indicated. If the same reaction works as shown here, we should get vinyl ether over here. Of course, it is pretty much known that these compounds produce the CC bond formation rather than the CO bond formation, but still the allene intermediate is same, whether you proceed through CO bond formation or CC bond formation, the same allene intermediate will be forming. And then when you look at this, if this R equal to hydrogen, we still have active methylene proton, it intuitively underwent enolization, therefore that OH will cyclize with the sp carbon to give this kind of a furan. But if R is not equal to H, the reaction didn't proceed beyond allene. Allenes are the end products. Then what we thought is, if you use a base, because there is a methyl ketone here, this time we make the enol from this side. So we use a DBU and then enol formed on this side, and then that cyclizes to give sterically hindered dihydrofurans. Similarly, once this allene is formed, if you introduce aniline to this reaction, now enamine will be forming here, like oxygen oxocyclization happen here. Once you introduce the aniline here, azocyclation can be possible. Therefore, that gave us, if R equal to H, I am talking about this one, we got the dihydropyridines, and R is not equal to H, we got the sterically hindered pyrroles using this strategy. Continuing on the same, we switched this 1,3-dicarbonyl to cyclohexyl acetyl, 2-acyl cyclohexanones. That gave us to generate benzofuran derivatives and tetrahydroindoles using the same concept. However, we do not have any proof on this particular case that this reaction is proceeding through vinyl propargyl ethers, because we couldn't isolate, and we also believe that this is not through propargyl-Claisen rearrangement. In continuation of optimization reaction, we have taken this acetyl acetone and propargyl alcohol, and then we could able to make this furan, where we are adding a DBU and generating enol. During these studies, we also observed there is a tricyclic scaffold formed as indicated here, almost less than 5% yield. This reaction was not surprising to us because we predicted and it proceeded as desired, but this was very pleasing to us because this is not expected product. And starting from an acyclic systems, we could able to make a tricyclic scaffold, which is more interesting. And then when we try to understand the reaction mechanism, when you have the alene form, the calcium will activate this dicarbonyl system, and the orthocarbon of this particular benzene offers an intramolecular Friedel-Crafts annulation, and the carbanion that is producing here will add to this carbonyl carbon which is activated. Therefore, you generate a strained cyclobutane, and again you have a enol and a carbonyl compound. Therefore, this underwent in situ intramolecular aldol reaction followed by elimination to give the fluorinol molecule. We propose this cyclobutane because there is a CC bond breakage happening, and this is one of the possible way that if you have a ring strained ring, so then you can indicate the CC bond breakage to get such molecule. We also proved that if I don't have a benzene ring, the reaction stops. And if you block these two orthocarbon, the reaction stops. That means you need a orthocarbon for intramolecular Friedel-Crafts cyclization. Interestingly, there are some natural products having biological relevance, having this kind of a scaffold, more or less, diaryl, though the hydrogen is in different position. So we thought that to develop a general strategy, instead of addressing one molecule total synthesis, we thought let us develop a strategy for the family of these natural products. And then our optimization conditions suggest that you just take these two substrates and treat with calcium triflate in DCE reflex conditions. That will give the fluorine, diaryl fluorines as shown here. And if you have a para-substituted phenyl here, the two orthocarbons are equivalent, therefore the single isomer is forming, and if you block one of the orthocarbon, there is only one orthocarbon that can offer us the Friedel-Crafts cyclization. There was no issue. But when we have a meta-substitute benzene, two chemically inequivalent orthocarbons are there as indicated here. Therefore, a mixture of products are formed here in a different ratio, different distribution. And then we also tried to show some synthetic applications of these compounds. So we did allylation of this alcohol and then subjected to Claisen rearrangement. Therefore, C allylation happened. Again O allylation, and then we got the diene. We subjected this diene to ring closing metathesis using Grubb's second generation catalyst to give this kind of a scaffold. Now what we observed is, as for showing synthetic application, this is all right, but we were not happy. The reason was the tricyclic scaffold was synthesized in a single pot. Just to add one extra ring, we are doing 1, 2, 3, 4 additional steps we are doing it. So then we revisited our strategy. Our starting material was, we were just taking this and making the fluorinol. But if you see, still there is an enol here. If I add one more propargyl alcohol to that, we can generate a propargyl ether again. Therefore, that will undergo propargyl-Claisen rearrangement to give a tetracyclic scaffold. Let it be this or this, that doesn't matter. But still, we should be able to make this scaffold is a single pot. With that idea, we have optimized the reaction conditions, and we found that if you use excess of propargyl alcohol, basically you need to add one more propargyl alcohol over there. So we used excess of propargyl alcohols and just reflexed in calcium Lewis acid, and then we could able to make this sterically hindered indinopyrons in excellent yields. The reaction was quite general. And we also introduce iodine over there to functionalize, pre-functionalize this hydrogen. And we also observed that these compounds exhibit acidochromism. When you add TFA to this compound, it underwent ring opening to give a highly conjugated system like this, which shows a brick red color solution. And the moment you add a triethyl element to this one, then it comes back to the ring closure and becomes colorless. And in another multi-component approach, we were trying to do, we in situ produce alpha aminoketone. You take alpha ketoaldehyde and add corresponding amine so that you produce alpha aminoketone. Activate that with a Lewis acid calcium. Now this electrophilic the electrophilicity at this carbon enhances. So electron rich arenes, you can do arylation over there. Once you do the arylation, the azi anion can be trapped with activated alkyne. The resultant carbanion that is produced can be added to the activated carbonyl compound. With that idea, we could make C2-aryl pyrroles. And if you replace the activated alkyne with a benzene, you can make C2-aryl indoles. And then you can also use alkynoids instead of this triple bond. So you can make still C2-aryl indoles. And you can also make pyrroloquinolines using this strategy. And when I define arene as trihydroxybenzene fluoroglycinol, now I see there are several hydroxy centers available. Therefore, if I add excess of propargyl alcohol, these systems can again undergo propargyl-Claisen rearrangement, like as shown here. So excess of propargyl alcohol gave the bis propargyl ethers, and that underwent again propargyl-Claisen rearrangement to give naphthopyrans, benzene fused with pyrans on both sides. Therefore, it's like a two-fold propargyl-Claisen rearrangement on a single pot. In continuation, at some point, we were looking at a different type of propargyl alcohol, and this reaction come across where the alylation on these systems has been performed using a palladium catalyst, where they have protected the alcohol, activated the alcohol with bark, and nitrogen has been protected and allyl tributyl was used. At parallel time, we also developed a reaction where you take an alcohol and alkene, alpha methyl styrene, you can do a dehydrative cross coupling to do alylation on this carbon. So we thought that a similar alylation on these systems can also be performed without activating this, without protecting this, without use of any allyl tributyl tin or palladium. Just take a calcium based Lewis acid, you just take this substrate and take an alkene using calcium, then we could do the alylation of these oxindoles. When we looked at this molecule, it is not just alylation, but this is a perfect substrate that can undergo, it's a Cope type rearrangement, 3,3 sigma tropic rearrangement to give an allene of this kind. And then if the cyclization is possible, then you can expect an exo or endocyclation to get these kind of scaffolds. With this idea, we have optimized our reaction conditions and found that when we have taken this propargyl alcohol and if we heat the reaction at 70 degrees, we are getting the 1,5-enines. Once 1,5-enines are obtained, we are raising the temperature to 130 degrees Celsius because these are thermodynamically favored thermal reactions. Therefore, we could make the cyclopentenes as expected. Interestingly, when there was a hydrogen here, we also did CH functionalization if we have excess of corresponding tertiary tertiary alcohol. This is usual that you generate a carbanion here, and then you can also do alkylation over here. In continuation, we were successful in making this cyclopentenylation, but the student also observed that if we manage the temperature at 110 degrees Celsius, he could detect the hexadiene, spirohexadiene. Although isolation of this spirohexadiene is not that easy, therefore we trap this hexadiene in a Diels-Alder cycloadation by adding a malic anhydride to this one. So then in situ we started here, and from here to here we could make this kind of a sterically hindered, if you see there are 5 stereogenic centers that can be visualized in this molecule. And we have generalized this reaction. So you do the reaction at 70 degrees initially to get the 1,5-enine, and then raise the temperature by adding malic anhydride so that you can construct this kind of a scaffold. In addition, if you see, we were able to trap this hexadiene in the Diels order, all right. But if you see this CH2, that is still having an acidic protons, acidic carbon, as indicated here. Therefore, electron deficient system, you can actually do some kind of a ring rearrangement if you can take up that proton. Using that idea, we added chloranil to that substrate, and then this underwent ring rearrangement to give phenanthridinone as shown here. Of course, phenanthridinones are known to have a biologically important background. With that, we could generalize this reaction to synthesize variety of phenanthridinones. Of course, we also added simple naphthals to oxindole derived propargyl alcohol to generate naphthopyrans, thinking that it is still through propargyl-Claisen rearrangement, because we didn't isolate the propargyl ethers, but still we believe that it is proceeding to propargyl-Claisen rearrangement. We also did some preliminary Alzheimer's studies for these planar scaffolds. With this, what I showed you is, we were successful in demonstrating propargyl-Claisen rearrangement beyond allenes, not starting from the propargyl ethers. That is the point one. And we really do not have success on propargyl vinyl ethers, because in situ it was not possible to form it. However, because the problem is this one. Instead of ether formation, we believe that this is what is happening. Although even this was not isolated, but we believe that a CC bond SN2 prime reaction is happening, so that directly allene is forming. However, using mechanochemistry, what we noted is, you start with a propargyl alcohol, take activated alkyne, you grind these two with a DMAP, in situ we could produce the vinyl propargyl ether. Now this vinyl propargyl ether underwent cyclization to give the furan, and then it also produced the pyrrole as indicated here. So the we got
Karthik. Munduku randi. Shiva Nagaraju.
Okay, anyway. So we have some preliminary results, and I am sure that at some point I will show you that using mechanochemistry we could solve this issue, where we could not solve this vinyl propargyl ether propargyl-Claisen rearrangement. So in mechanochemistry we have some results, and at some point we should be able to disclose that. So with this, I again say that we have expanded the scope of propargyl-Claisen rearrangement beyond allenes by the in situ formation of propargyl ethers, where we have isolated it, and we have extended to introduce the polycyclic compounds that we can be synthesized, which the most of the times the reactions are very simple Friedel-Crafts reactions we have used, and then the synthesis generally commences with readily preparable or readily available small materials, and most of the times we use calcium based Lewis acid catalyst. And with this, I thank you all for your kind attention, and I thank University of Hyderabad and funding agencies. Thank you all.
Yeah. Thank you very much for your very nice interest of calcium. Actually, very nice work on a calcium catalyzed reaction. And sorry for that, because you're perfectly on time. Okay, there are some questions, comments. Yes.
Just a small query. When you are doing this Claisen rearrangement, okay, you have something like a fluorine type of moiety,
right?
OH, one side methyl, and then another methyl.
Right.
So I just want to know, like, how the steric plays in the reaction efficiency. Yeah, the second reaction. So how efficient? No, top one. Yes. How efficient are those?
This one, no?
No, top. This one, yes. Are these very efficient reaction? Like,
see, this one without catalyst, these are known. Phenol propargyl ethers.
I just want to know, because
there are the steric index. There was no issue. Only thing is you need to raise the temperature to really 180 and 24 hours.
Yields are good.
I didn't mention yields were good. I don't know. I missed it, but yields were good. Yes.
Okay. We need.
Because other Claisen arrangements happens at 100 degrees, right? But this needs at 180, and other one works in 2-3 hours, but this needs 24 hours. Maybe that's the reason.
Yes.
Yeah, Srinivas, nice talk. So I have a question related to your the use of calcium as Lewis acid. So did you try all the other available Lewis acids and found calcium is best for these reactions, or how did you figure out calcium triflate is the best Lewis acid for the reaction?
Yeah, we did. We have the optimizations.
Okay.
Not too many Lewis acids we have studied, but we did studied calcium, generally scandium, ytterbium. There are 5-6 other Lewis acids, lanthanide based things.
Okay.
We do study, and then we found the beauty of this thing is those catalysts do not work efficiently under solvent-free conditions,
Okay.
and this calcium particularly works best in solvent-free conditions.
Okay.
So that is the advantage.
Did you also consider the possibility of triflate coming out and picking a proton from the solution, because you have protic medium, right? And then thereby a triflic acid
Triflic
catalyzes
acid
Bronsted
forms.
acid activation?
Yeah, see if there was somewhere I showed you the pyrrole and pyridine formation.
Yeah.
In that paper, actually reviewer asked same question. Then we have used a proton sponge 2,6 ditertiary butyl pyridine,
Okay.
and then proved that triflic acid is not forming there. We have taken
so
care
it is
of
a
it.
Lewis acid activation.
Right. Lewis acid activation.
Thank you.
Yeah, thank you. Yeah, just taking words, I had the same question. I was wondering with bismuth, have you tried, or indium chemistry on that?
No. The reason is we are focusing, we do study some Lewis acids. We wanted to highlight this because of its less toxicity, natural abundance is more of calcium.
Yeah.
And it has its own advantages compared to other scarce
Yeah, and you did the
catalysts.
control experiment with triflic acid,
Right,
of course,
right, that
as,
we did,
as it
yeah.
was asked. What about chiral ligands?
What is that?
Chiral ligands on calcium?
No, we didn't try. We use generally calcium trifluoride and calcium triflates. And we use tetrabutyl ammonium PF6 as a counter anion.
That's what I saw,
happens is there is a ligand metathesis takes place in case of triplet.
Yeah.
So then you generate more Lewis acidic calcium species in situ, and that is the active catalyst.
I was thinking of binaftol or...
Chiral we haven't tried.
Yeah, binaftol, you never tried.
No, we didn't try.
That's interesting.
But there are few groups from Canada, they are working
They're
on
doing that, yeah.
but these commercially available calcium catalysts are really expensive, so we haven't tried.
Yeah. We have a question here, Thomas.
Thanks for a very nice talk. So it's still about the asymmetric calcium chemistry. You did not investigate nitrogen ligand on calcium to increase the acidity, and then you can use PyBox to do some chiral chemistry?
We haven't tried.
Because there is a report from Kobayashi, he used calcium diodide
Yes.
as a Lewis acid in combination with the Lewis base, and he has been able to do some Mannich reaction.
Right.
So you
There are
might get this,
right. Even from Canada, Professor Antilla has more than a dozen asymmetric reactions on calcium-based catalysts. We haven't tried. As I mentioned, we never thought of making in situ those, but the commercial catalysts are really expensive, so we haven't tried. And most of the times, our systems underwent aromatization very quickly, so we lose the centers. For example, here, yes, you can still have a center, but most of the times our molecules are aromatized.
Okay,
You
thank
can-
you very much.
Here, yes.
Thank you very much. So we are going to close the session, and please join me to thank the 4 speakers who really did excellent presentation. No, we have the ceremony. Yes, we have the ceremony, and after we will have the tea, coffee break.
Long live India and France friendship.